Okay, so now we're going to look at the Gauss-Legendre methods, which are an important class of collocation-Runge-Kutta methods. And they are in some sense the highest order methods it's like you might expect to get. And they're based on this corollary of the error analysis we had done for collocation methods. Right, so let's say you have C1 to CS be the roots of some polynomial PS, which is in the space of polynomials of degree S on T, that are orthogonal to, well, I should say orthogonal with respect to what kind of weight function, with respect to the weight function omega t, which is just identically 1, okay, on the interval t between 0 and 1, okay. Then the sort of corresponding collocation method is of order 2s, okay. And the proof is, of course, a trivial application of this more general result we had established before, because what it means for this polynomial to be orthogonal with weight 1 is basically that PS paired with T T to the J, if you will, right, is equal to 0. Well, let me just write what that is, which is the integral from 0 to 1 of PS T to the J dt, right? So this is equal to 0, right, for J equals 0 to m minus 1. Actually, not m minus 1, is actually s minus 1, right? So that's actually what is meant for this polynomial of degree s. It's like to be an orthogonal polynomial is that it's orthogonal to all the lower degree polynomials. Okay, and so that's what happens, and of course that basically means that this satisfies the conditions for the theorem before, but with a case where m is equal to s, and then the order of the collocation method then is s plus m, which is of course 2s in this case. Right, so that just sort of proves that if you construct one of these, it's like collocation Runge-Kutta methods using collocation points, which are roots of this, orthogonal polynomial, then you're going to have, it's like a Runge-Kutta method, it's like for order 2s, okay, which is really, really nice. So these methods are called Gauss-Legendre methods, okay. So the sort of S stage 2s order collocation Runge-Kutta methods are referred to as the Gauss-Legendre methods. And they have a large number of very, very nice properties, which we'll talk about later. Okay. So we proved basically a while ago when in the lead up to studying orthogonal polynomials, it's like and the applications to quadrature, that the roots of these orthogonal polynomials, it's like are strictly contained with the interval from 0 to 1, okay, and they're distinct. Okay, so that's nice, right? So so from before, the roots of PS are distinct and contained in the interval basically 0 to 1. Okay, so you could, of course, it's like construct these orthogonal polynomials using the Gram-Schmidt process, sort of generalized, if you will. It's like to function spaces, which is what we discussed before. But it turns out there's also an explicit formula for these orthogonal polynomials. Okay, so there is a general formula. Okay, so there is an explicit formula for PS of t, right? And you can obtain it by basically rescaling. It's like the what are called the Legendre polynomials can be obtained by rescaling the Legendre polynomials, which are orthogonal polynomials with, again, weight function, which is identically 1, but over the interval from -1 to 1. Okay, so you basically have to, shrink the interval, it's like by half, and then sort of shift it to 0, 1. Okay, and so let's write down what that polynomial PS is. Okay. And to make it well defined, it's like we're going to essentially normalize this polynomial so that it is monic, which is to say that the leading order term is 1, right? Has a coefficient 1. Okay, so PS of t is equal to s factorial divided by 2s factorial. And then this s factorial is squared. And then there's a sum from k equals 0 to s of -1 to the s minus k. There's a s choose k term, and then there's a s plus k choose k term, and then there's a t to the k. Okay, so this is just something, of course, you can compute. It's like relatively easily. That gives you the sort of the monic version, it's like of the orthogonal polynomial. So that's sort of a normalized version of the orthogonal polynomial where the leading coefficient is 1. And then, of course, you have to compute the roots of those orthogonal polynomials. And we had proved, it's like before, that those roots are guaranteed to be in interval from 0 to 1. And they're guaranteed to be distinct. And so, of course, you can use this to construct one of these collocation Runge-Kutta methods, which we talked about before. Okay, so let's look at some examples of these Gauss-Legendre methods. Okay, so I'm just going to leave this formula up for a little bit. Okay, so for s is equal to 1, right, this orthogonal polynomial p1 of t is just given by t minus 1/2. Okay, so that immediately tells you obviously that it's just a linear term. The root of that, of course, is just 1/2, so c1 is 1/2. Okay, and then you can write the method in the following way: 1/2, 1/2, and 1. Okay, and this is, of course, nothing more than the implicit midpoint rule. So this is the implicit midpoint rule. Okay, and for s is equal to 2, right, the orthogonal polynomial p2 of t looks like t squared minus t plus 1/6. So you can figure out what the roots are. The roots are, one of the roots is 1/2 minus root 3 over 6. and then another root is 1/2 plus square root of 3 over 6. So you can check that, one property, if you will, it's like of the roots of these, it's like orthogonal polynomials for weight function 1 over the interval from 0 to 1 is that they're symmetric about half, okay? And it really just comes from the fact that the Legendre polynomials, which we talked about before, which were these orthogonal polynomials, but over the interval minus half to half, are symmetric about 0, okay? Let me rephrase that. The roots of them are symmetric about 0, okay? And so what's going to happen is that you're going to have, so it's easy to see, of course, that these pair of roots, it's like are symmetric about 1/2, okay? And that's a general phenomena, and of course if you have only one root it has to be at 1/2 as well. So you're seeing examples of this symmetry of the roots. It's like about this 1/2 property. Okay, so you know what the collocation points are. It's like, and then of course it's like you just plug it into the expression which involves integrals of the basically the Lagrange polynomials associated with these points, and then you have to integrate them either from 0 to 1, it's like for the BI coefficients, or you have to integrate them from it's like 0 to CI, it's like for the AIJ coefficients, right? So and so on. Okay, anyhow, so when you do that, it's like for these points, it's like you get the following method. There's a 1/2 minus root 3 over 6, and then it's 1/2 plus root 3 over 6. There's a 1/4 here. This is a 1/4 minus root 3 over 6. And then there's a 1/4 plus root 3 over 6. And then there's a 1/4 here. Okay, and so it's like you see, it's like, that it has the first order, it's like order condition, which is to say that the row sum, it's like of the matrix A is equal, it's like to the corresponding C value, which is something you see here. And the other property, of course, is that the row sum, or the sum of the B entries, it's like sum up to 1, okay? And of course you can go on, but I won't. It's like sort of belabor the point. Suffice to say, it's like there is a explicit expression. It's like for the degree S orthogonal polynomials, and then it's like once you compute that, it's like you can find the roots of the polynomials. The roots of the polynomials have this property of this orthogonal polynomial has this property that it's symmetric about the 1/2, so that makes life a little bit easier. And then once you have, it's like the collocation points, you can then use them to compute, it's like the full Runge-Kutta matrix, which is what happens here. So let me just stop here for now, and we'll talk more about the Gauss-Legendre method as the quarter progresses.